Hello again, this is online class 8. We're going to talk a little bit about section 5.3, a little more today about 5.3, and also go on to section 5.4, which of course is entitled Mean and Standard Deviation for the special case of the binomial distribution. We'll see today that the formulas developed in section 5.2, it turns out they can be greatly simplified in section 5.4. Again, that's only if you can justify having a binomial distribution. Alright, it's Friday, October 12th. This is fall 2012, and of course we're in Math 125 at SUNY Cobleskill. Excuse me. Alright, let's talk a little bit about 5.3 again. Let's say you're given a binomial procedure or experiment with 4 trials, and the probability of success in any given trial is 0.7. And let's say I want you to construct a probability distribution for x, where x equals the number of successes in these 4 trials. And we're going to use a table to summarize this probability distribution. And all you really need to do here is make a table, list all the possible values of x. Now, x, if you're talking about 4 trials, excuse me, x can be one of 5 values. 0, 1, 2, 3, 4. Now, we've seen this table set up before. Well, it's somewhat similar to probability distributions we saw in section 5.2, but each of these probabilities are determined by the binomial formula. So what I'll do is use the binomial PDF command, and I'll take 4 successes. The probability of success in any one trial is 0.7, and I'll let x range from 0 to 4. Right. So basically I iterate this formula 5 times to fill in this table. I've already done this. If you grind out the 0 case, I get 0.0081. Of course, I won't write this for all 5 cases. I think you get the idea. The 0 case will yield me that number, and basically I then let x equal 1, let x equal 2, let x equal 3, punch it out, and let x equal 4, and this is the result. So when I ask you to construct a probability distribution in this type of scenario, this table format is what we're looking for, again, in this binomial scenario. Alright? Alright, recall the binomial PDF command, npx. The PDF stands for probability density function. Alright, and this gives me the probability, of course, you know, of x successes in n trials. Well, you already know that. Now I want to talk about this. I know I talked about it in one class, but did not talk about it in another class. So please forgive me if you're reviewing this again. I want to look at this other command in the distribution list on your calculator. binomial CDF. This stands for cumulative distribution function. The syntax is the same, but the result is very different. The C, the cumulative, the C in CDF means that you're just adding up all the cases of the given X value that you enter and below. So this is really the probability that X is less than or equal to whatever value you plug in. So it adds up the X case and all cases below as well. Let me give you a simple example of this. Again, suppose any number, one number is as good as another. We'll use the ones we used above. If you're in a binomial experiment, binomial procedure, and you got 4 trials, the probability of success in any one trial is 0.7. Let's say I want you to find this. Find the probability that X is less than or equal to 2. Now, you know and I know that you can tediously add up the probability of the 0 case, the probability of the 1 case, and the probability of the 2 case. And you'll have to iterate this binomial PDF command 3 times to get this result. Alright, with this binomial CDF command, oops, let me erase that. With this binomial CDF operator, binom CDF, and you'll find it in the distribution menu on your calculator, as we talked about in class, depending on whether you have the 83 or 84, the actual label in the distr list may differ. You'll find it right next to the binom PDF command. If I plug in 4 and 0.7 and 2, this is the probability that X is 0 plus the probability that X is 1 plus the probability that X is 2. The calculator is programmed to grind this out automatically. All right, I can shorthand this in this fashion. I can claim this then is also the probability that X is less than or equal to 2, because X has to be 0 or more. And you punch this out on your calculator. Well, instead of grinding out this formula 3 times, you can get it with 1 series of button pushes, and the calculator returns 0.3483. Alright, we can easily see the beauty and use of this command. This is useful in, at most, or at least, scenarios in a binomial procedure. Again, if you don't have a binomial procedure, you can't use these above formulas, alright? Alright. Binomial cumulative distribution function. Alright, let me work out an example. It was in the homework in section 5.3. I'm going to edit it a little bit. This is number 37 on page 227. You'll be familiar with it as the watching NBC Sunday Night Football exercise. Please pause now and turn to that problem, number 37 on page 227, and please refamiliarize yourself with that example now. Please pause now. Alright. you'll recall we've got 20 trials. We're asking 20 people, did you or did you not watch Sunday Night Football? We're calling watching NBC Sunday Night Football a success, and the probability of success in any one trial is 0.22. All right, I'm going to change this problem a little bit from as it's stated in the text. Let's see. I'm going to call it Part A, Cap A. It's a little bit different than the Part A, little a in the book. I'm going to say find the probability that at most 5 in 20 are watching NBC Sunday Night Football. Okay, I'll shorthand it like that since we've already talked about the problem. I'm hoping you'll follow. Again, we're randomly selecting 20 people, as stated in the problem. Find the probability that at most 5 in 20 watch NBC Sunday Night Football. Well, what does at most 5 mean? Well, that means 5 or less, right? So we've got a binomial experiment with these above mentioned parameters, and I really want the probability that x is less than or equal to 5. Now, of course, if you desire, you can add up all the 6 cases of x using your binomial PDF command. Right? You'll have to punch out the 0 case, the 1 case, the 2 case, 3 case, 4 case, 5 case. You'll have to iterate that binomial PDF formula 6 times, from 0 to 5, right? I claim I can get all this pretty much in one iteration if I use the cumulative distribution command, binomial CDF, with 20 trials, a 0.22 success in any one trial, and just plug in the x value of 5, and the cumulative distribution function will automatically add up all the cases of x below 5. And I punch that out, and I get 0.734, really with one touch of the button, or a few touches of the calculator buttons. Much easier than grinding out the PDF formula 6 times, I think you'll agree. If you want to confirm that you get the same answer by punching this binomial PDF formula out 6 times, please, I invite you to do so. But I think you'll agree the value of this is evident in at most or at least situations. Let me give you another one here. Again, I'm going to edit the problem as stated in the book. Again, I'll say find the probability that at least 10 in 20 are watching the NBC Sunday Night Football, or NBC Sunday Night Football, right? Well, let's see. What does at least mean? At least 10 means 10 or more. So this is what I seek here. Again, we're still in the scenario with 20 trials, and little p is 0.22, right? Well, I think you can appreciate, if I want to use the binomial PDF command, I'm going to have to work this formula out 11 times, from the x equals 10 case to the x equals 20 case, right? 10, 11, 12 through 20. That's going to be 11 cases, 11 possibilities for x here. This is too cumbersome. But if I use a little finesse and my binomial CDF command, I think we can work it out quite a bit easier. Let me make a note here. Because we're dealing with the probability distributions, the sum of all probabilities has to equal 1. So if I add up all the probabilities from x equals 0 from all the way to x equals 20, I know I'm going to get 1 when I add all those up. So I could say this, erase that equal sign, the probability that x is greater than or equal to 10 is going to be equivalent to 1 take away the 9 or fewer cases, right? And this probability that x is at most 9, I can get this with the binomial CDF command, can I not? Let me write it out for you. Remember, x is greater than or equal to 10 is going to be 1 take away the 9 or fewer probabilities, right? So I'll do binomial CDF, not PDF, CDF, and put in my above mentioned parameters, 20.22 and 9. The computer, the calculator, would automatically add up all the values, all the probabilities for values of x less than or equal to 9. And I grind this out very easily with essentially one iteration of the binomial CDF command. Much better than doing it 11 times with binomial PDF, right? Alright, we'll call that slight addition to 5.3 done. Let me get a new layer here. And I want to go on now to section 5.4. Section 5.4 is entitled The Mean, Variance, and Standard Deviation for binomial distributions. As we mentioned before, earlier in the section, if we can justify a binomial distribution, if we can give proof of that, we can make these formulas for mean and standard deviation quite a bit easier than those we see in section 5.2. Let's recall those formulas for section 5.2. 5.2 was entitled Random Variables, and we ground out these formulas for mean of a probability distribution. You recall this is equivalent to the expectation of a probability distribution, and this formula wasn't too bad. It was basically the summation of each possible x value times its associated probability, right? That wasn't such a big deal. Again, these are reviewing the formulas we saw in section 5.2. I made a mess of that. Hang on a minute. Let me erase this whole thing here. Again, recall section 5.2, the random variable section. We established formulas for mean of a probability distribution and standard deviation of a probability distribution. And the mean formula wasn't too bad, but the standard deviation formula was kind of nasty. Too many people got it wrong on the online exam, so please be reminded it's going to be on the test on Wednesday, right? Basically, you square each possible x value, multiply those squares by the associated probability, add up all those products, and then subtract the previously computed mean. Okay. So certainly these are formulas that work in general for any probability distribution, and you'll need to memorize these and apply these on test on Wednesday, right? All right. It turns out in a binomial experiment, or the book calls it a binomial procedure, these formulas can be greatly simplified. And I think you'll agree that standard deviation formula can be kind of nasty, especially if you've got 6, 7, 8 different values for x. Basically, you have to make a table and grind out the squares of x values, multiply by the probabilities, etc. It takes rather a long time to get it right. If you know you are in a binomial procedure, in other words, you've got a fixed number of trials, you've got 2 outcomes per trial, right? I claim the mean of a random variable in the binomial case is simply n times p. Well, that's not a whole lot simpler than summation x times p of x. I think the real beauty of this comes through when we grind out this standard deviation. All it is the square root of n times p times q. Now, I'll talk about the motivations behind these greatly simplified formulas in our next face-to-face class on Monday. Right? But I just want to grind out a few examples of using these formulas, greatly simplified formulas, in a binomial case here in the online class. Let's say motivation. Let's say you've got a 20 question multiple choice test. All right. Let's say in this multiple choice test you've got 5 choices for each of the 20 questions. I'll say random selections are made on each question. Okay. And I'll say find the mean. Value for the number of correct answers in the 20 questions. Well, I don't think this is too tough. I think most of us, I have a frame here. Most of us would say, well, if you got 20 questions and you got 5 choices per question, basically the probability of any one question being correct is 1 out of 5, and 1/5 times 20 is 4. I might expect 4 correct answers in 20, again assuming random selections. All right, we can formalize that. This is indeed a this is indeed a binomial experiment. You got 20 trials. If you're calling a correct answer a success, then the probability of success in any one trial is 1/5, or I'll call it 0.2. And that's enough to find this value of the mean in this binomial experiment, or binomial procedure. So the mean for the number of correct is going to be mu, and very simply it's n times p, so it's 20 times 0.2, which is, of course, 4. Alright, so what this is saying, in the long run, if you take this experiment, if you perform this experiment, in other words, take this test and make random choices on each question without knowing anything, you can expect, in the long run, 4 correct answers out of 20. Alright. Not too hard to, not a stretch to believe that, I suppose. Alright, let's find the standard deviation for my number of correct answers. Well, again, as long as you're in a binomial experiment, this formula is greatly simplified. All you do is compute the square root of n times p times q. Alright, so let's grind it out here. We've got 20 trials. 0.2 is my probability of success in any one trial. And if p is 0.2, remember q is the probability of failure. So q is the complement, the probability complement of 0.2, which is of course 0.8. And if I grind that out, I get a standard deviation of 1.79. Very simple. If you remember the problems from section 5.2, with drawing a table, adding a third column, getting a lot of products, adding up those products involving a square root, and subtracting the square of the previous mean, etc. Very much easier in a binomial distribution. Okay. Alright, let me work out an example here using these formulas. I want to look at exercise 17 on page 233 in our text. So please pause now and familiarize yourself with that exercise and come back when you're ready. Please pause now. Alright, exercise 17 talks about voting. And with our presidential election coming up, maybe this is a good thing to talk about. In the past presidential election, the actual voter turnout was 61%. In a survey, 1,002 subjects were asked if they voted. Well, if you were going to write a column with 1,002 possible, actually 1,003 possible values of X successes, from 0 all the way up to 1,002, you'd be here all day and all night. Alright, if you're going to call a success equal a voting, someone says that they did vote, then the probability of success in any one person is 0.61, because they tell us the actual voter turnout was 61%, right? Alright, part A asks us to find the mean and standard deviation for the numbers of actual voters in groups of 1,002. Right? Well, this is clearly a binomial procedure. You've got a fixed number of trials. The probability of success doesn't change from trial to trial. You've got 2 outcomes per trial. Either you vote or you didn't vote. And all the trials are independent of all the other trials. In other words, the probability of one person voting does not affect the probability of another person voting. Alright, so I'm going to say a binomial procedure is justified in the context of the problem, so we can apply our very simple formulas now. Again, this is you can only use these formulas in the binomial scenario. Well, you take your number of trials, multiply by the probability of success in any one trial. So my expected or mean number of voters in 1,002 based on this given information is 611.2. You write that down. The mean for the number of voters in 1,002 is going to be equal to 611.2. In other words, we can expect if we're going to perform this experiment, excuse me, namely ask 1,002 people, did you vote? You can expect in the long run, theoretically, 611.2 persons will say, yes, I did vote. Okay? All right, we also want to grind out the standard deviation. And again, thankfully, very thankfully, this formula is greatly simplified in the binomial case. So it's going to be 1,002 times 0.2 times, 0.61. Hang on a minute. I was thinking about that other example. It's up screen, so I missed it. You got 1,002 voters. The probability of success in any one voter, in any one person, I should say, is 0.61. The probability of voting in any one person is 0.61. So that means the probability of not voting is going to be the complement of that, 0.39. Alright, so I grind that out on my calculator. Let me make sure I'm crunching this out here. 1002 times 0.61 times 0.39. And the square root of that mess, I get 14, I'll call it, no, 15.4. Alright, so that is my standard deviation for the number of voters in 1,002 adults. So let me write that down. SD for number of voters observed in 1,002 adults surveyed is going to be 15.4. Okay. So again, very simplified formulas in the binomial case. Let me get another layer because I want to answer part B in this question. Again, this is the same exercise, exercise 17 on page 233, part B. Well, let's take a minute to read that. In the survey of 1,002 people, 701 said they voted. Wait a minute. 701 people said they voted. Whether they voted or not is another story. The book tells us the actual number of voters is 61%. And the book asks us, is this consistent? With the actual voter turnout, or is this result unlikely to occur with an actual voter turnout of 61%? Why or why not? All right, to make this the right conclusion here, we're gonna refer to our familiar idea of what is usual and what is unusual based on your given data. All right, recall. According to guidelines given throughout this textbook, any data within 2 standard deviations of the mean is usual, and anything outside these boundaries is unusual. So what I'm going to do is grind out the boundaries for usual behavior of our data, and if 701 falls outside of that range, I'll claim then, no, this is not consistent. Alright, well, what is our mu value? Well, you'll recall it's 611.2 was our mean, and our standard deviation was 15.4. Alright, so I can grind out my lower boundary, taking 611.2 and subtracting 2 times 15.4, and I'll get a lower boundary for my usual behavior of 480.4. Similarly, I can find an upper boundary for my label of usualness. So I'll take that mean, I'll take that mean and I'll add 2 times the previously computed standard deviation in this binomial experiment, and I get 642.0. So again, let me clean this up a little bit. So again, based on that 61% actual voter turnout, these are the boundaries for a usual number of voters in 1,002 surveyed adults. Again, this is based on the actual turnout. Alright, so clearly is 701, is the claim of 701 voters consistent? And of course we say no, because 701 clearly lands to the right of the upper boundary here, and we claim is unusual based on guidelines given by the author. So I'll summarize this like this. I'll summarize it like this. The claim of 701 voters out of 1,002 surveyed is outside the range of usual values based on the actual voter turnout of 61%. Okay? So, in short, the answer to part B is no, it is not consistent. Alright, we're approaching the 38-minute mark, so I'm going to call it a day. Hopefully everything will go smoothly, no major problems up till now. And this concludes online class 8, section 5.3 and 5.4 for Math 125 in fall 2012. That is all.